going to talk about Coulomb's law today, and essentially the force between two charged objects is given to you through Coulomb's law. And in the applet that we used last week, we studied two variables that change the force. We looked at the distance between the objects that are charged and then the size of the charges. And Coulomb's law tells us the size or the magnitude of the charges because of those two things, or due to those two things. So if we look at Coulomb's law, it might look scary at first, but it's really not. And I would suggest taking a few notes on your page 5 or page 6 on your packet. And so we're going to notice a couple of things about this. We're going to notice that it looks a lot like things that we've seen in the past. It actually looks a lot like gravitation, which is a good thing. All right, so our F stands for force, which is measured in newtons. And then we have this K here. That K is simply a constant. And that constant value here is 8.99 times 10 to the 9th. Notice that's really, really big. This jazz right here, that's all a unit. You really can just ignore that. It just makes the unit of force come out as a Newton. All right, so then we continue moving on. We have Q1 and Q2, so those are the charges on each of the objects measured in coulombs. And then we have this R on the bottom, which is the distance between the two charged objects. So that's how far apart those are, and that's going to be measured in the unit meters. So as we look at the direction of the force, we know that the like charges are going to repel and opposite charges are going to attract each other. And those forces are actually directed along a line that connects the two charges. And then the direction is going to be determined upon whether they're like or unlike. So let's say I have these two charges that are shown here. I've got a positive 3, and remember that micro there? Remember what that means? That micro coulomb means 10 to the negative 6. So we could rewrite Q1 as 3.0 times 10 to the negative 6 coulombs. And then Q2 would be negative 1.5 microcoulombs again times 10 to the negative 6 coulombs. Okay, so since Q1 is a positive charge and Q2 is a negative charge, those are going to attract. And we know from our applet work, our simulation, that these two forces are going to be the same size. They're going to be in the opposite direction. And in this case, they're going to be pointed towards each other because they are going to attract. And they're going to attract, again, because they have unlike charges. One's positive and one's negative. All right, so I think we are ready to try an example problem. So here is our example problem that we're going to try to do. So what I'm going to ask you to do is I'm going to ask you to pause the video at this point. So I want you to pause the video, and then I'm going to ask you to read that problem. I want you to draw the vectors that represent the forces that are acting on Q1 and Q2, and then we'll come back together in just a moment. So pause the video, sketch this out in your notes, and then draw those two forces in. Sorry, y'all, that was my husband just needed to tell me something. Okay, so back to where we were going. Those two forces are going to be attractive because they are unlike charges. They are towards each other like this, and they're going to be the same size. And the size is going to be dictated by Coulomb's law. So let's rewrite Coulomb's law, which is going to be our force is equal to, and I'm going to go ahead and put that constant on top because I feel like that's going to be easier to deal with than having it popped out front, divided by r squared. Okay, so at this point, you're going to go back and look at how big your k value is. Do I know how big my k value is? We do know how big our k value is, right? Our k value is that 8.99 times 10 to the 9th, right? So we know that's what our k is. And then we are going to substitute in our values for Q1 and Q2, and then r squared. So two things that I want you to pay attention to. Remember that micro there means 10 to the negative sixth. And you're also going to need this distance here in the unit of meters. So I'm going to ask you to pause your video. I want you to try this through all on your own, and then we'll meet together at the end. Okay? Okay, here we go. So here's our equation, and then we're going to go ahead and substitute in. The substitution looks like this. So I've got my Coulomb's constant we just talked about, 8.99 times 10 to the ninth. And then I've written out my Q1 as 2.5 times 10 to the negative sixth coulombs. Remember, I told you that we needed to pay attention to that. Here's something you definitely need to pay attention to. In our diagram here, that Q2 is negative, but did you notice I didn't put that negative out here? Our equation just gives us the size, not the direction. So do not put in the negatives in your equation. You're just going to put the sizes of your equation, or the size of your charges in the equations. You do not need to put the negative sign. And the other thing you need to pay attention to is that distance down there needs to be that 5 centimeter distance, need to be in meters. So we changed that to meters as being 0.05. And then remember to square that denominator. That's an inverse square law. When you do that math, you will come out with an answer of 45 newtons. That's a huge force for an electrostatic force. But note a couple of things about this. First, you want to notice that when you're typing these into your calculator, remember to use that scientific notation button. It usually is going to look like this in your calculator, like 8.99, and it'll say E, or sometimes it'll be a lowercase e to the ninth. It typically on our TI calculators is above the 7. Sometimes on our Casio calculators, it looks like 10 to the x, something like that. Just remember, we've done that a bunch of times, and you're going to want to use that function. If you have trouble with that, try it a couple of different ways until you get that answer correct. The other thing that I want you to notice about Coulomb's law in general is how it looks so much like our gravitational law. So our gravitational force law looks like this. It was gravitational force, I called it G, is equal to, and then it was a capital G times M1 times M2 over R squared. This is our universal gravitation. Notice it's in the exact same format as our electrostatic. There's not a coincidence there, right? A coincidence? I think not. Those are really fundamental laws of physics, and they follow the same form. So I feel like that's something that you need to pay attention to and understand as well. All right, I hope that helps you. What I'd like you to do now is to try some of those practices on page 10 to get you through learning how to use Coulomb's law. All right, great work.